Hello folks, this is Jim with Science Talk. I want to discuss with you changing CO2 levels. Now this graph here, courtesy of Climate Central, goes back approximately 800,000 years, kind of looking over the glaciation periods and so on. And basically, this is parts per million on this scale here. And as we see, it goes up, it goes down, up and down, almost cyclical. That's probably due to Milankovitch cycles, with a major explanation for it. And then when we get to about 1910, 300 parts per million, which is pretty much just about what the highest that's been previously recorded over the past 800,000 to a million years or so. But now look what's happened in the last 107 years. This is what we have data for. It's gone vertical, right? Increased 108 parts per million. And it's continuing to go up here. I've seen recent measurements from 411 to 420 parts per million. So, as I've stressed before in other videos, it's the rate of change that is the critical concept to bear in mind. Now, I've done some recent examination of the literature to look at what past CO2 levels have been. This is due to a certain exchange of correspondence I had and so on. And in so doing so, some of the papers have reported levels around 520, even 760 parts per million, some as high as 2,000 parts per million. A word of caution. The authors themselves state in their article that the measurements are extremely imprecise, and thus the results are not to be taken as being definitive. What do I mean by that? Well, let me back up and kind of to explain this. Let me give you an illustration. I did a video on statistics earlier where I discussed the bell curve, and that if I have 95% of if I look at the bell curve, 95% of the data, the area under the curve represents the percentage of data contained. That 95% of the data would be between 2 standard deviations below and 2 standard deviations above the mean. But what is often done is that we construct what's called a 95% confidence interval for the mean, meaning that we calculate a range of values. And the range of values indicates what? That 95% of the actual values of the mean itself will fall in this range. 95% of the time, the true mean can be found in this calculated interval. Let me throw some numbers at you to kind of illustrate this. Let's say I'm doing something, I'm measuring whatever, and my mean is 150. It could be, say, milligrams per kilogram body weight, whatever it might be. And using the standard deviation, we can then calculate the confidence interval, 95% confidence interval for the mean. We can do one for the 99% as well, but let's just stick with 95 for this example. And my range is suddenly 20 to 280. Whoa. That means within that range, from 20 to 280, we can find the mean 95% of the time in that range. That's all. That is a wide range. That's all over the place. I could have another situation, though, where my 95% confidence interval for the mean might be, say, 142 to 158. Now, that's a nice narrow range. That means we have a good handle on the measurement. We've gotten good data, we've gotten good precision, if you will. Basically, the smaller the standard deviation, smaller will be the confidence interval around the mean, which means the results are more accurate. In these papers, we're looking at these values that are all over the place. The confidence intervals were huge, meaning that the results are not all that reliable. So you have to look at these things critically. You can't just say, "Whoa, this study says 760, so it must have been 760 in the past." Look at the CI. The CI, in these cases I was looking at there, the CI went from, what was it, about the 520, I think it went down as low as 100, and it's shot all the way up to 900. So it's a wide range. It's not precise. In other words, it's not settled science. Now, yes, they were looking at ways to measure this, but the further back in time you go, the more difficult it is to do such measurements. This is not too far back in geological time. We can look at ice cores, we can look at sediment cores, where we look at the forams, the diatoms, radiolarians, and all that kind of stuff. I did a video on isotopic fractionation discussing that. Please check that out. So basically, we lose, because of plate tectonics, a lot of the material, the information that we found in the sediment cores goes into the subduction zone and is lost. So we have to try to infer. Yes, we can take some samples. Yes, we can try and measure some isotopic activity or, other indications of biological activity, and from that extrapolate outward. But as you can see, that is not very precise. So in my view, I look at those values with a grain of salt, and it's not settled science. This here is settled science because we have verified these values through numerous techniques. Oftentimes, the stuff in the past has been based on one technique and with really insufficient sample sizes. This is no fault of the scientists. They're trying the best they can do, and that's why in their reports they basically say these are imprecise. We're just trying to get a handle on things, and it may not be correct. So these are CO2 levels. I will now want to show you something here. Okay. This is basically starting from here's that 800,000 years ago, and this horizontal line right here is the average temperature based on, as you can see right here, and this is in Fahrenheit, based on the 1960 to 1990 average. That's what the average temperature is. And we're basically using that as a baseline to compare. And so what are we seeing here? Let's look at this peak here. If I go back to the previous slide, that peak here, where it is warm, corresponds to that peak right there. Okay. It goes down to here. And look, CO2 levels go down. Oops, wrong way. So now, if I come up to here, we see another peak. And lo and behold, there's another peak. In other words, the CO2 and the temperatures track very, very nicely. Look how warm this is. And does it surprise you that we see that peak right there? Right? 400,000 years. Make sure I lined that up right. Yep, 400,000 years. Next one's about 300,000 years. Here's that other peak of 300,000. So we show very nicely that as CO2 levels go up, so do the temperatures. Another word of caution. It's not just CO2 that determines temperature. It's also methane. Remember, I had discussed with you in previous videos how you may have one or more independent variables controlling the response in the dependent variable. Okay. Earth's temperature is the dependent variable. CO2, the concentration of CO2 is an independent variable. The concentration of methane is another independent variable. And this is where we do statistical analyses to ascertain the contribution to the response each of the independent variables make. So, Earth was really warm in the past. We do have evidence for that. There was also methane being released from clathrates, so forth. Plus, the Earth was still basically a radioactive ball. It was still radioactive heat being given off as well. We have to consider that as to why the temperature was so much warmer in the past. So, I wanted to, and here's an interesting thing. Look at this right here. Okay. That's this right here. The LGM was called the last glacial maximum. And we start warming. Now they did a little break in the graph here, so that my scale is different. Here were the increments of 200,000 years. Here is 5,000 years, because we can refine our measurements for that. Now, if you go back, if we were to fit like a straight line here, and boom, it was like if I was to do a regression through these points to about here, and then it kicks up. That's the basis for the so-called famous hockey stick graph that Professor Michael Mann at University of Pennsylvania created to show the levels of CO2 changing. But look at this. We see this rise here, and we can pinpoint this right to the start of the Industrial Revolution. So, as I said, with these peaks, when the temperature warms, the CO2 goes up. Temperature cools, the CO2 goes down, and so on. We just see this all throughout. Now for the next, I would say, disturbing graphic. Monthly carbon dioxide sets a new high. In other words, looking at per month from the years 2013 all the way through 2018. So this is for data right up to the end of April for 2018. So they basically measured an average CO2 concentration per month, January, February, and so on. And what do we see going on here? It keeps going up and up. And kind of follows a sine wave, sort of similar to when I did that sea ice video. And because there's going to be cyclical variations in the CO2, there will be some seasonal effects. But you can see we're pumping more and more. In fact, if you look right here, at the end of April, it has crested the 410 parts per million indicator. So basically, this is showing we're just dumping more and more CO2 into the atmosphere. Now, this is a very interesting graph. Temperature anomalies over land and over ocean. So we have 0.0. 0.0 is the baseline average. So anything that goes below the baseline will have a negative value associated with it. Anything above it will have a positive associated with it. If we follow the lines themselves, right, okay, with the sort of like an orange square here, that's land surface temperature. With the blue square, that's sea surface water temperature. Okay. We call it SST, sea surface temperature. We don't put the water in there. We know SST, but sea means water, right? Sea surface temperature, SST. The smoothing is basically running a regression, if you will, through this. More technically, it's more of a Fourier smoothing function. That's getting technical, but that's we're trying to fit some sort of a function through these points here. And as you can see, starting from 1950 and going to basically looks like up to about 2015 or so, we see that, you know, they track pretty closely up until about 1980, and then the air starts warming up more so from the average. But so does the sea surface temperatures. Not as much. Why is that? Specific heat. It takes more energy to warm up this water than it does air. So if I have the same volume of air here and the same volume of water here, it takes less energy to heat up that air by a given amount, say a degree Celsius, than it does to heat up this same given volume of water, 1 degree Celsius. It takes more heat energy. Why it takes things a while to boil. The fact that water sea surface temperature is still half a degree, maybe it looks like more 0.6 degrees above the average, indicates the enormous amount of energy that has been imparted into the system. This is not insignificant. This is hugely insignificant. Hugely significant. Hugely significant. And as you can see, we're approaching that 1.5 threshold. Well, they agreed to 2, but more the science is basically saying we need to keep it below 1.5 degrees. This is what they're talking about. We're approaching that, keeping the planet to 1.5 degrees or less than of our warming activities. So a lot of the energy is going into the water. Anyway, I hope you found this video informative, but I wanted to show you how we have really strong collaborative data showing very nicely how CO2 and temperature levels track, so that if anyone tries to tell you that that's not the case, you can basically call out BS on them. The data is solid, and there's collaborative data, not just from ice cores, but from sediment cores, tree ring dendrology as well. Whereas we go way, way back in time, often using just one technique, huge error involved, the numbers are not that reliable. So yes, you may hear these reports about these levels there, but keep that in mind. The science is not settled on that. Science becomes settled, then I'll be glad to say, okay, we've got definitive data that indicates that such levels were in fact in existence millions and millions and millions of years ago. But looking at this here, looking at the CO2 levels we're dumping in, looking at CO2 versus the temperature, we definitely have solid evidence that humans are doing this. And also remember, way, way back in years past, Antarctica was not at the bottom of the planet. The Earth cooled down significantly once Antarctica went to its current location, because that also changed ocean currents and heat distribution for the planet. Antarctica is the planet's refrigerator. All that ice reflects a lot of heat energy back into space. So, yeah, Earth was probably much, much warmer in the past, but it was because of methane, it was because of the position of the continents, and the currents and the heat distribution and so forth. Yes, there was some CO2. Yes, there was a lot of methane, but there was other physical parameters at work in addition. The big changer was Antarctica. That has cooled down the planet. Imagine if Antarctica was not where it is and we're doing what we're doing. We probably would have killed ourselves by now. So thank you for your time. I hope you found looking at these graphs informative. You can always pause the video and scrutinize them in more detail if you're so inclined. But thanks for watching. Please share. Hey folks, just a reminder to please subscribe and click the bell so you know when I drop a video. Please share my videos. Please tell others of my channel and of the work that I do. I also hope that you will consider becoming a patron at patreon.com/Science Talk with Jim Massa, where from time to time I upload videos there exclusively for my patron subscribers. Details in the description box below. Thanks.